I would like to welcome everybody to the inaugural session of the Maryland Robotics Center Future Leaders in Robotics and AI, Celebrating Diversity and Innovation Seminar Series, sponsored by Microsoft DC Metro Engineering Site. Today, we have two exciting speakers. The first will be Dr. Mengxue Hou, who will be talking about assured abstraction for robotic hierarchical planning. And the second speaker will be Dr. Ali Nellis, who will be talking about agent-environment interactions for uncertainty reduction and communication. Each talk will be a 20-minute presentation followed by 5 minutes of questions, and we've budgeted a couple of minutes to transition between talks. Before we get started, I would also like to point out that you can find a list of all of the talks in this series on the Maryland Robotics Center website and on the YouTube page. And the recordings will also be available on the webpage and the YouTube page. Recordings on the YouTube page, announcement of all of the talks on the MRC site. So moving quickly into our first talk, it is my pleasure to introduce Dr. Mengxue Hou, who received the PhD degree from Electrical and Computer Engineering at Georgia Institute of Technology in 2022. And before that, received her bachelor's degree from Electrical Engineering at Shanghai Jiao Tong University, Shanghai, China in 2016. Since 2022, Dr. Hou has been working as the Lillian Gilbreth Postdoc Fellow at Purdue University. Her research interests include robotics, mobile sensor networks, and shared autonomy. So please take it away, Dr. Hou.
Thanks. Thank you for Professor Ati for introducing me. And let me share my screen. Okay. It is my great pleasure to be invited to this seminar series and to be the first speaker in the series. So today I want to talk about my past research in robotic decision-making. Recent years, in a lot of robotic applications, we need the robotic system to make real-time decisions in an environment full of uncertainty. And most of the time, the environment is unstructured, meaning that we don't have very much prior knowledge on how to parameterize the environment. Here I'm giving two examples. One is autonomous driving. The uncertainty will come from whether pedestrian will cross the road or what actions the other vehicles will take. And on the right-hand side, this would be a underwater vehicle sampling the eye of the hurricane. And again, the environment is very complicated. It's difficult to give accurate model to avoid uncertainty in this case. So my past research focuses on the marine autonomy, how to enable underwater vehicles to make smart decisions in the unknown ocean environment. And if we consider underwater vehicles, there are mainly two sources of uncertainty. The first one comes from prediction of the environment. As you can see in this video, the ocean flow field is very complicated. It's very difficult, or it's impossible to have an accurate model to describe the ocean process. And another source of uncertainty comes from localization. The underwater acoustic localization is, again, a very challenging problem. And we will not be able to get perfect localization information, meaning we don't know exactly position of the vehicle. So these two sources of uncertainty leads us to POMDP, or a continuous partially observable Markov decision process formulation. Here on the right-hand side, I'm showing a general mathematical formulation for a POMDP. We have the system dynamics, which can be nonlinear. I'm using the F to represent a general nonlinear function. And then omega K would be the process noise, or in the case of underwater marine autonomy, it will be coming from the imperfect prediction of the environmental process. And then the vehicle position or the system state cannot be directly known. Then we need to get to know the system state through this observation equation. And I'm using H to denote the detection model. And then NK would be the localization uncertainty. And so in POMDP literatures, usually they will define the belief state as the posterior distribution of the system state, conditioning on all the historical observations. So the continuous state POMDP is equivalent to our infinite dimensional MDP. To solve the planning problem on a belief space, usually it would require 2 steps. The first step would be to derive a finite rank approximation model of this infinite dimensional MDP. So from data, we can get this finite rank approximation or representation. And then the second step would be, given the representation, we can design a planner that solves the POMDP problems. But then there are a lot of existing research or existing algorithms that can solve the POMDP. All of them will require parameterization parameterization to describe the continuous posterior distribution. So even though they all can guarantee optimality of the solution, the scalability is an issue. This is the well-known curse of dimensionality problem for POMDP formulations. So in robotics community, there is actually an existing approach to deal with scalability issues, that is by developing abstraction or developing model reduction to describe the system. In my talk, I will use interchangeably the term model reduction and abstraction. So what is model reduction? On the left-hand side, I'm showing a very simple illustration. That is, if we want to describe a system in 3D, then we can project it to 2D, and then we will have a reduced order approximation model to describe the dynamics. And we have a lot of applications in robotics that involve designing such model reduction approach. Examples can be a mobile robot, the traversability analysis. Usually we will need to parameterize the domain through piecewise constant cells so that we can reduce the complexity of the traversability analysis. Also, autonomous driving, in many cases, we need the robot or the vehicle to make decisions from the image it receives. We don't directly use the image to design the optimal policy. Instead, we derive this kind of scene graph to represent the vehicle's knowledge about the environment. This is also another kind of model reduction. But what is the challenge in model reduction? Well, by deriving this reduced order approximation model, we actually are making the decisions based on a different set of understanding about the environment. If the reduced order approximation model is very different from the actual physical process, then this can severely degrade the performance of the planner, and it can lead to very bad consequences, especially for safety critical systems like in autonomous driving. So it is really important to derive a high fidelity reduced order approximation model so that we can guarantee the performance of the planner. So the contribution of my research is in 2 parts. First of all, from the data, I'm developing this learning-based non-Markovian model reduction approach to derive a high fidelity abstracted representation of the system. And then taking advantage of the abstraction, I develop an iterative hierarchical planning algorithm that can guarantee to find the optimal solution in the abstracted model without excessive requirement on the computation cost. Because of the time limit of this talk, I will focus on the contribution of the first part on deriving this model reduction approach. So because we want to deal with this model reduction error, so let's look deeper into the model reduction problem, and let's see where does the model reduction error come from. So here I'm using this operator MK to represent general nonlinear system dynamics, and xk is the system state. So suppose the MK, this operator defines the system evolution in the 3D space. How can we approximate the system dynamics in a 2D space or in this lower dimensional space? A very natural idea would be, how about we project this push forward operator also to the 2D? And then in this case, we will have this one-step approximation or the Markovian transition model. to describe the reduced system dynamics, right? This is a very simple idea, but then if we compare the result we get from this one-step approximation with the actual ground truth, which is directly projecting the trajectory of the system onto this lower dimensional space, we will see that they're different. And the reason is that this unmodeled system dynamics, which is the system evolution in the z-axis in this toy problem, is coupled with the reduced state in the 2D space. And we are ignoring this coupling. So this leads to the difference between the ground truth and the Markovian transition model. So because we know the model reduction error comes from this coupling, so how about we improve the fidelity of the model reduction approach by modeling this coupling and adding the coupling to the reduced order approximation model? But then the challenge is, to do this, we will need to know what is the error state, or the difference between the actual or the full system state and the reduced state. But the problem is the error state may be high dimensional. Like if the original system is of 10D and then the reduced state is 2-dimensional, then the error state is in an 8-dimensional space, which is still require a high computation cost to estimate and compute. So the solution is actually comes from the Mori-Zwanzig formalism. That is, we can use a set of time delay embeddings of the resolved state or the reduced state to approximate the error state. And I will not show the mathematical formulation of the MZ formalism, but here are the two references for the formulation and the mathematical derivation. So with this intuition, let's go back to the continuous state POMDP problem and see how we can leverage the insight from the MZ formalism to help us build a better approximation model for the belief dynamics or belief abstraction. So again, we have the actual belief dynamics, which is the evolution of the posterior distribution. Here, I'm using the operator L to represent the Bayesian update, and the operator T to describe the prior dynamics. The Bayesian update would depend on the observation received by the system at every time step. And then this prior dynamics would depend on the control action, or UK, taken at every time step. In my past research, I use specifically the piecewise constant basis function to parameterize the belief state, which is shown on the right-hand side. We have a partitioning algorithm that can assign higher discretization resolution to the part of the domain where the system state most likely will visit. I will ignore the details in this talk. So what do we mean by the Mori-Zwanzig-based belief abstraction? We are basically trying to find the coupling between the historical time steps and the future time steps reduced state. This coupling is described by this memory kernel, the function G. If we find this coupling, then we can derive this non-Markovian abstraction method that can help us predict what would be the system dynamics in the reduced order space. So, but how can we compute or approximate this memory kernel? If we look closer into this function G, we will see that the memory kernel depends on two parts. The first one is the Bayesian update at every time step. And then the second term would be the prior dynamics. Even though there are many existing approaches to approximate or to compute the memory kernel, they are all for the special case where the system dynamics is time invariant. So it still remains to be an open problem that how can we approximate the MZ memory kernel in the case of POMDP, where it depends on historical observations and control actions taken by the system. So my research will address this open problem. So as we see, the memory kernel depends on two parts. The first part is it is dependent on the control action. And the second part, it also depends on the observation received. So my idea is, why not we separate this problem to be two subproblems. In the first problem, I will try to find a model of this non-Markovian memory kernel as a function of the applied control input of the system. And then the second problem would be how we can incorporate the online observation to define this Bayesian update in the parameterized state space. So this is the main idea. For my solution to the first problem, we use LSTM to approximate the memory terms in the MZ equation. So the reason why we use LSTM is that it can capture this non-Markovian effect of in the system dynamics, and also it avoids the vanishing gradient challenge, which is commonly seen in other types of recurrent neural network. So in order to train the LSTM, we would need the input-output data pairs as the training data. And as shown by the MZ formalism, the input data would be the reduced state or the resolved state at historical timestamps. And then the output would be the difference between the actual reduced state and the output from the Markovian model. So with this input-output pairs, we can train the LSTM by solving a regression problem that is minimizing the difference between the LSTM output and the actual output data in the training set. So we have the algorithm, or we have the solution to the first problem. And then second, we need to incorporate the Bayesian update to compute the belief state from the prior distribution. So we developed this very simple approach, which is we also parameterize the likelihood function with the same set of basis function we use to parameterize the prior distribution. And then we will have a Bayesian updating law, which is element-wise operation in each cell of the domain. So to summarize, we take two steps to develop this MZ-based belief abstraction algorithm. So to model the prior dynamics, we use this LSTM-based prediction, taking insight from the MZ formalism. And then the second step is to define this approximated Bayesian update in the reduced space. And then with the posterior distribution, we can leverage any existing symbolic planar in the belief space to solve the planning problem. So I want to emphasize that this is the first effort in applying the MZ formalism to robotic applications, where the memory kernel is dependent on both the action and the observation received by the robotic system. So we have the algorithm. Now, the second question to ask is, how does the incorporating the memory effect help us in deriving the regarding the fidelity of the reduced order approximation? So we want to give theoretical justification on the model reduction error. We define the model reduction error as the difference between the actual belief state and the belief state generated from the proposed algorithm. And then we bound the model reduction error in two steps. The first step, to bound the model reduction error by decomposing it into two terms. So the first term is the error from modeling the prior state using the neural network. And then the second term comes from the approximated Bayesian update. So with some effort, we find a bound on the model reduction error for the proposed algorithm. And then it's very interesting because this upper bound on the model reduction error, it actually does not explicitly depend on the time, does not depend on the time step K. If we look at the upper bound on the model reduction error, if we use the Markovian transition model, we will see a time growing term in the upper bound. So this actually shows the benefit of incorporating modeling for the memory effect using the learning-based method. And it justifies that by the proposed algorithm will improve fidelity of the reduced order approximation model. We also did some simulation to validate the performance of the algorithm. So again, I'm considering underwater vehicle navigation problem. And I'm using this particle model to represent the system dynamics, and also considering how the ocean flow field will affect the vehicle speed. So for the observation, I'm using a binary detection model to describe acoustic localization. And then the planning objective would be to minimize the travel time for the vehicle to start from the initial distribution to reach a target set with high probability. And we compare the proposed algorithm with algorithm that use Markovian transition dynamics to describe the belief state, which is the generalized cell mapping method. And we are comparing two criteria. The first one is the computation time. It is how much time each of the algorithms take to return a solution. And also, we are comparing the total cost of the solution returned by each of the algorithms. We take A star or omniscient at A star as a lower bound on the comparison. By omniscient, I mean the A star algorithm knows additional information than the other two algorithms. It knows exact position of the vehicle and also exact flow speed in this domain. So from the comparison, we see that the proposed algorithm can achieve comparable solution quality regarding the total cost as the generalized cell mapping method, but it can reduce the computation cost to find the optimal solution. And we also changed the discretization resolution we use to describe the belief state. For the GCM, we consider 50 times 50 grid cells and also 100 times 100. We do the same for the proposed algorithm. We see that the computation cost will increase if we use finer discretization resolution, which makes sense because this finer discretization resolution, we will need larger number of parameters to describe the system dynamics. But again, the increase is not very significant. So this concludes my talk. In the beginning, and I raised this question that how we can enable real-time robotic decision-making in the unstructured and unknown environment. So in my past research, I developed MZ-based model reduction approach to describe the system dynamics. And given the abstraction, I also developed this hierarchical planner that can guarantee to find the optimal solution. So combining these two parts, I can provide a decision-making framework that guarantees assurance. That is, it can guarantee to find the optimal solution, but also can scale up to higher dimensional systems. So I want to quickly mention my future research. So in my future research, I want to extend what I mentioned before, this decision-making framework, to a multi-agent scenario, or more specifically, how to enable human-robot collaboration to explore unknown environment. So following the same idea, I will develop my future directions in 3 steps. The first step would be to extend this learning-based abstraction method to multi-agent scenario, which would be a distributed perception problem. And then the second step would be to design a distributed planning strategy for task allocation and motion planning. Then the third thrust would be how we can directly learn useful strategies from data or active inference problem. And because of the spirit of this seminar series, I want to quickly mention my experience and thoughts about promoting diversity. So in my past research, in my past study as a PhD student and also as a postdoc, I've participated in many teaching and mentoring activities where I mentored many students that comes from underrepresented groups in STEM. Here I'm showing 2 pictures of undergrad students that I mentored in their research course. Both of them did wonderful work. And as an international student and a female student, I understand like minority students coming from underrepresented groups, they may have difficulties getting familiar with the environment in the research community. So I've related with my personal experience to help them get over the challenges they experience. And I was also an active participant in the Women in Engineering Society and also the K-12 outreach programs like the AB7G, which is algebra by 7th grade when I'm at Purdue. So going forward in my future career as in academia, I will continue to participate or to lead activities that can promote diversity and inclusion by building a research program with this welcoming and inclusive environment for the students coming from underrepresented groups. So thank you. This is all of my presentation, and I would love to take any questions.
Thank you. You only hear a few of us clapping, of course, because most of the participants are not able to speak, but we have some great questions in the chat. So first of all, Mengxue Hou, she asked a question, is it possible to apply the proposed algorithm for a high-dimensional system? What will the computational complexity be with respect to the dimension?
Yeah, this is a very nice question. The complexity would be dependent on the number of partitions or the discretization resolution used to parameterize the system. So for my past research, I'm only able to demonstrate this algorithm specifically for underwater vehicle applications where the system is 2D. But definitely it will be part of my future research directions to see how well does this algorithm generalize to other problems with higher dimensional dynamics.
Great, thank you. And I have a question, which if you have covered and I happen to miss, I apologize, but to me, it looked like kind of the dynamics in the kind of flow fields were roughly static over time in the examples that you were looking at. But at the very beginning of your talk, you showed one where they were kind of changing over time. So what are your insights and thoughts about extensions to this work that would deal with kind of changing over time?
Right, this is a very nice question. With this learning algorithm, actually, it is not able to adapt over time. But then my idea would be we can add in another layer, which is modeling this temporal variation of the environment with less number of parameters, not a neural network or more like adaptive control algorithm. So in this case, we will be able to model the long-term variation using the LSTM and then quickly adapt in short term with this a more simple model, a model to represent the system.
Okay, thank you. And I have one other question about the final slide where you're showing kind of your outreach efforts. I saw the Georgia Tech Autonomous Blimp in the background, I believe. So have you found that to be a good kind of training platform for bringing in, people that are new to the community and getting people up and running?
Definitely, it is a very nice platform. And actually, this is developed by my PhD advisor and the lab, I did my PhD. And we actually find this is a very nice platform for human-robot interaction and human-robot collaboration because it has very long duration of flight. And also, humans feel safe when being close to the blimp. It's not like drones where you might get hurt. So yeah, it's a very nice platform for both education and for research in human-robot collaboration.
I totally agree. The quadrotors for somebody that is just learning to use a robot can be quite, I guess we have big nets, right, to help people from that, but the balloon seems a lot nicer. Anyway, thank you very much. That's all the time we have for questions, but I will remind everybody that after the talk, we're going to have kind of a meet and greet for everybody to talk with both candidates.